Hello everyone, this is our third class of quantitative techniques. In the previous two classes, we have studied about the history, applications of operation research. We have studied about the LPP, linear programming problem. In the last class, we have formulated a problem into a mathematical form. Now, what we have to do, we have to solve this problem by any of the method which is applicable in the LPP. There are two methods to solve an LPP. One is graphical method and another one is the simplex method. So what are the topics we have to cover here? That we have to cover that what are the methods, and we will solve an LPP with the help of a graphical method. So as we discussed, there are two methods to solve an LPP. One is graphical method and second is simplex method. Now where we have to use the simplex method and where we have to use the graphical method. Simplex method can be used in any of the situation. Either we have two variables, four variables, six variables, three variables. But your graphical method cannot be used where we have more than two variables, because whatever we plot in a two-dimensional figure. So the graphical method can be used only if we have only two variables. So if we have more than two variables, we cannot use graphical method and we have to use only simplex method to solve that LPP.
On a graph, we will use a coordinate plane. We know that there are four quadrants in a coordinate plane. As the decision variables in a linear programming problem should satisfy the non-negativity constraint, the values of x and y should not be less than 0. It means they will lie in the first quadrant only. Therefore, to solve these problems on a graph, we need to use only this quadrant. For better understanding, let's solve this linear programming problem graphically. In this problem, we need to find the maximum profit, which is denoted by the objective function z is equal to 50x plus 18y. So let us find the values of x and y which satisfy this linear inequalities. As the solution needs to be found using a graph, let's represent these inequalities on a coordinate plane. How do we graph inequalities? We will first write the corresponding equations for these inequalities. Can you write them here? That's right. These are the corresponding equations. Next, we need to graph the lines of these equations. And we can do that by finding the coordinates of x and y intercepts. Let me help you with the x and y intercepts of the first equation. For the x-intercept, we substitute y equal to 0. We get the value of x as 50. So the coordinates of the x-intercept are 50, 0. And to find the coordinates of the y-intercept, we substitute x as 0. That gives us the value of y as 100. The coordinates of the y-intercept are 0, 100. Similarly, we get the x and the y-intercepts of the second equation. With these points, let's draw the two lines representing these two equations on a graph. Let's mark the 4 points first. With this, the first line can be drawn like this. It represents the equation 2x plus y is equal to 100. Likewise, let's draw the second line representing this equation. Give it a try. Here's the line representing the equation x plus y is equal to 80. So how will this graphical presentation help us find the optimal solution? We will first mark the feasible region of this graph. Do you know what a feasible region is? It's the common region determined by all constraints of a linear programming problem. Each point of a feasible region satisfies the linear inequalities of the problem. So, let's mark the feasible region for this problem. If we consider only these two linear constraints, all the points of this quadrant will satisfy the given inequalities. And hence this entire quadrant can be the feasible region. However, if we consider these two constraints as well, the feasible region will get restricted to the region O, A, B and C. As you can see, the two lines intersect at point B 20, 60. The region within these four corner points is the feasible region of this problem, as each and every point of this region will satisfy the linear constraints of the problem. For instance, let's take the point 30, 40. If we substitute these values for x and y respectively in the linear inequality x plus y is less than equal to 80, we will see that the point satisfies the linear inequality. In this way, every point within and on the boundary of the feasible region can be the feasible solution for the given problem. It means the points on and within the region satisfy the linear constraints. Then how will we find the optimal solution? Since there are many possible solutions for this problem, we will use the corner point method to find the maximum profit. Now, what's a corner point method? In this method, the solution of a linear programming problem lies on the corner point of a feasible region. The coordinates of the corner points are substituted for the values of x and y in the objective function. In this example, points O, A, B and C are the corner points of the feasible region. We will evaluate the objective function by substituting these points as values of x and y one by one. First, let's find the value of z at point O. The coordinates of point O are 0, 0. 50 times 0 plus 18 times 0 gives us 0. Likewise, can you fill in these values of z? For the second point, we get the value of z as 1440, 2080 for the third, and 2500 for the fourth point. So we have all the four values of z at the corner points of the feasible region. Since our objective is to maximize z, the optimal solution lies at point C 50, 0 because the value of z is maximum at point C. This is how we solve a linear programming problem graphically.
So the summary of this class is what we have studied here. We have studied the method to solve an LPP, and we have studied the graphical method. How to solve an LPP with the two variables by a graphical method. Now the questions for the practice, when we started this class or when we end the last class, the questions were that how to solve an LPP. So in this class, the when I said that there are the two type of method to solve an LPP, the first question is what is the graphical method, what is the simplex method. And when I said that if two variables are there, then we can solve the method problem with the graphical method. So the question comes that if there are more than two variables, that what will happen? So if more than two variables, then we can solve the problem with the simplex method. Now the next question is, okay, we have solved the problem by the graphical method, that what is the simplex method? So simplex method can be discussed in the later classes. Now this is all about this first class, third class. So at the end, these are the references, so you can find out this graphical method in the last two books, because in the very first class it is not very much explained how to solve a LPP by the graphical method, because in the first book the approach is different. They have solved the problem by Excel solver, which we will discuss later. So in the two books, which is I mentioned at the second and the third point, you can find out the solution of a LPP by graphical method in a good way. Thank you so much.